Hi. Good morning, everyone. My name is Satya. Currently, I'm working as a tech lead at Fifth Third NAC. Based on my experience, today I'm going to talk about the architecting secure and scalable integration platforms for FinTech. Based on my experience, I'm going to talk it. I have around 17 years experience as a Java backend developer with the cloud and various database. So in this today, agenda is the fintech integration challenge, current integration landscape, security compliance framework, advanced data protection, scalability architecture patterns, balancing act, security, compliance, performance, implementation roadmap, and key takeaways. So basically, the fintech integration challenge, understanding the unique demands and evolving requirements for integration platform. For example, while developing microservice development, communication between two microservices, sometimes the communication is asynchronous or asynchronous communication. It is a big challenge. And the current integration landscape, exploring the existing ecosystem, key trends, and modern fintech. For example, the legacy application was developed in many other technologies, but the modern applications were using developing latest technologies and also deploying to cloud. This is also one of the integration challenge. Security compliance frameworks, implementing robust identity access control API security measures, and advanced data protection strategies for encryption, tokenization, data masking to safeguard sensitive information. For example, while doing transforming any payment transaction, for example, we want to mask, we want to encrypt the account numbers, sender account number and receiver account number. So in that case, we are going to implement encryption, tokenization, and masking the data in the while printing logs in the server. And scalability architecture patterns, designing the high performance systems with asynchronous processing, service message, event driven approaches. For example, if you want to increase the scalability, based on the application, we have to increase the scalable, the component size will be increased. Then only we can balancing act security, compliance, performance, achieving optimal integration solutions that meet all integration challenge. Provide comprehensive multi-tenancy support for diverse financial products, ensure data integrity, consistency across distributed system, seamlessly integrate legacy core banking system with modern microservices architecture, process high volume financial transactions with robust security measures, dynamically scale to efficiency, manage peak transaction volumes, facilitate rapid innovation and feature delivery while mitigating risk, guarantee compliance with dynamic regulatory frameworks. For example, PSD2, GDPR, CCPA. Current integration landscape, traditional challenges, modern requirements, the imperative for robust integration platforms. In the traditional challenges, high operation costs, drain budgets for innovation, brittle point-to-point integration, hindered maintenance and scalability, monolithic middleware, slows developments and market response, outdated perimeter security, leaves internal services vulnerable. In modern requirements, zero trust security authenticates and authorizes every request, embedded compliance supports dynamic regulators with automated alerting, real-time fraud detection, integrates AI/ML for immediate response, elastic scaling, leverages cloud-native auto-scaling for volume. API-first approach enables seamless third-party and open banking integration. The imperative for a robust integration platform, a robust fintech integration platform must enforce security, monitor compliance, and optimize performance. It needs to protect data, ensure regulatory adherence, and maintain low latency for critical transactions, all while fostering innovation. Distributed Identity Access Control 2.0, OpenID Connect, JWT, and implementation considerations. While using OAuth 2.0, the authorization frameworks grants third-party applications limited access to services without exposing user credentials. By using Springboard, I implemented OAuth 2.0. OpenID Connect, an authentication layer built on OAuth 2.0, enabling clients to verify user identity through essential profile information. JWT, JSON Web Tokens, a compact, self-contained method for security transforming information in between parties as a JSON object. Implementation considerations are establishing key rotation schedules and secure key management practices, and optimizing token lifetime for balance between security and usability, implementing scope-based authorization, granular access control, ensuring a financial grade API compliance for enhanced protection, integrating multi-factor authentication. These frameworks facilitate a zero trust model, ensuring every service to service call is authenticated and authorized, irrespective of network location. API gateway security controls, essential security functions, rate limiting, circuit breakers, request validation, web application firewall, authentication authorization enforcement, TLS termination, rate limiting, control requests to prevent DOS attacks, ensure fair resource distribution, and protecting services from overload. For example, while implementing REST, we can implement this rate limit. Circuit breaker prevents cascading failures by quickly failing requests to unhealthy services, maintaining system stability during high load. Request validation. For example, in the RESTful services, while sending payload, we have to validate the request validation, which fields are mandatory fields, which fields are optional values. In the request validation, we can implement those validation for all the fields. So validation to block malformed requests and injection attacks. Implementation secures communication and uploads, encryption, centralizing certificate management, and optimizing performance. Authentication authorization validates identity tokens and applies granular access policies, ensuring only authorized access to APIs. By using this, only authorized third parties only can access our services by using this authentication authorization. Even if it is an internal application, also we can implement authentication authorization. Web application firewall integration provides defense against common web vulnerabilities. OWS API by detecting and blocking threats. So by using a web application firewall, we can protect the application if we can secure the endpoint. So data protection methods. Data protection we can implement by using encryption, tokenization, data masking. Encryption utilizes AES-256 for data, HSM backend key management, TLS 1.3 for data transit. Implement forward secrecy to protect sensitive data with non-sensitive tokens that retain operational utility without inherent value. This is crucial for handling primary account numbers. For example, you can tokenize SSN account numbers, user ID, those things we can by using tokenization we can implement. Data masking, employ dynamic masking for non-production environments, enabling realistic testing with anonymized data. Apply techniques like format preserves, encryption, reduction for a highly sensitive fields. So in this access control, for example, core data protection, encryption, tokenization, and data masking. Protective perimeter, network security, monitoring, and TLS. Asynchronous processing architecture. In the asynchronous flow, we can implement API gateway, mobile pay, mobile queue manage, validation service, analytics engine, and transfer and notification service. So in the benefits for financial transaction for asynchronous decouples transaction efficiency from processing, improving responsiveness, enables batch processing for efficiency when appropriate, facilitates retries and data queues for resilience, allows back pressure mechanisms to handle tra- traffic spikes, supports compensation transactions for all failure scenarios. Implementation note. Financial transactions require guaranteed delivery and exactly once processing. Choose message brokers with strong durability guarantees and idempotent service mesh architecture. So by in the service mesh, we can see observability, security, traffic management, policy enforcement. A service mesh provides an infrastructure layer for handling service to service communication, offering critical capabilities for FinTech platforms. For example, observability offers comprehensive metrics, logs, and traces essential for regulatory audit trails and in-depth performance analysis. Traffic management enables sophisticated routing, load balancing, and fault tolerance without requiring application level changes. Security facilitates mutual TLS authentication, and streamlined certificate management at the platform level. Policy enforcement ensures consistent access control and rate limiting access all services within the mesh. Event-driven architecture. Event-driven architectures are ideally suited for financial transaction flows where every state change represents a critical business event. For example, Saga pattern coordinates distributed transaction across multiple services. Event sourcing stores state changes as an immutable sequence of events. CQRS separates read and write model optimized performance. Event streaming enables real-time processing for immediate fraud detection. This approach enables highly responsive systems that can scale horizontally while maintaining a complete audit trail for regulatory compliance. Balancing security, compliance, and performance. Striking the right balance among security, compliance, and performance is a paramount for fintech platforms. As the chart demonstrates, a hybrid approach combining event-driven architectures with a service base offers the most effective strategy to achieve robust security, comprehensive compliance, and exceptional performance. For the balanced security, we have the traditional monolithic basic microservices, API gateway, service mesh, event-driven mesh. So the key elements for balance, proactive compliance, layered security, optimized performance, observability, and traceability. Implementation roadmap. The phase one, implement API gateway with OAuth to OIDC authentication, establish secure CI/CD pipelines with automated security, deploy basic observability stack, metrics, logs, traces. And phase two, security hardening. Implement encryption and tokenization services, deploy secrets management solution, establish key rotation schedule, and scalability. Introduce message brokers for asynchronous processing, implement service mesh for inter-service communication, develop auto-scaling policies based on demand patterns. Advanced patterns. Implement event sourcing for critical transaction flows. Deploy CQRS for highly volume read operation. Establish chaos engineering practices to verify resilience. Key takeaways. Adopt a zero trust security model, leverage WAT to OIDC and JWT for end security across all integration points. This requires continuous verification and least privilege access at every layer, critical for protecting sensitive financial data. Embedded comprehensive observability into the platform to ensure operational excellence and streamline regulatory compliance. Robust logging metrics and tracing provide deep insights, enabling quick issue resolution, performance optimization, and complete audit trail for financial regulations. Implement layered data protection with encryption, tokenization, and make masking to safeguard sensitive financial data effectively. Protected data at rest in transit and in use with robust encryption, tokenization for desensitization, and masking for secure testing. Leverage event-driven architecture and service mesh, highly scalable and secure fintech platforms. Event-driven patterns enable real-time processing and auditing while a service mesh provides consistent traffic management policy enforcement and mutual TLS. Thank you. Thank you.